Recording. All right. Last class, we discussed what is the algebra curly A of observables. For the Klein-Gordon equation in curved spacetime. It had 5 main properties. First, products of fields belong to A. I should also add that the identity belongs to A. Second, which was the first in the last time I wrote, is how to add and multiply by scalars. Third is that the field is real. Fourth, it satisfies the Klein-Gordon equation. Where this means smooth and compact support. And 5, it is the commutation relation between the fields phi of f, phi of g equals to I e f g times the identity. So this was our main discussion last time. Besides this, we started discussing some important states. Namely, we discussed what is a vacuum in QFTCS. There are many possibilities. Not a single choice. And we require them to be Gaussian and pure. Where Gaussian means that the endpoint functions were such that the odd ones vanish and the even ones are given by Wick's theorem. All right. This is a summary of what we did last class. Are there any questions concerning last class?
Just a clarification, maybe.
Mhm.
So the fact that you're using a free bosonic theory is what implies the vacuum to be Gaussian, right? If you had chosen some sort of interaction, the vacuum did not be Gaussian, right?
Indeed. Then I don't think it would be possible to find a Gaussian state. I'm not completely sure, but I find it quite unlikely. Yeah, I don't see how you would be able to find a Gaussian state for an interacting theory. But this is not an
the notion of
implication. I am defining that a state is Gaussian if it satisfies these things, and there are many Gaussian states. So it is not an implication. It is I choose in a state that is Gaussian, but I can do this choice because the theory is not interacting.
Correct. But the notion of vacuum should also exist for an interacting theory, right?
Yes, but interactions are way more difficult to consider. It generally, I'm not really used with working with interactions in quantum field theory in curved spacetime, I mean. So
But is there a notion of definition of vacuum for an interacting theory? I mean,
I
not
believe so,
like
but the
this, but
algebraic structure gets way more difficult.
mhm.
It is probably going to be a perturbative notion of vacuum.
Okay. Yeah, okay. Thanks.
You're welcome. What you do in those situations, as far as I know, is you're going to define an algebra, and then you're going to define a correction to the algebra, which is going to be some B. Then you're going to define some more correction to the algebra, which is C or something like this. So you have a more complicated structure that I'm not going to dive into because I'm not familiar with it in details. In case you're interested in how these things work, what I recommend is the book by Kasher Eisner, which is Perturbative Algebraic QFT. It is fairly mathematical. There's also the 2015 paper by Hollands and Wold, which is a nice review. Any other questions? Okay, so I'm going to start discussing the next special class of states, which are thermal states. In usual quantum mechanics, a thermal state is given by a density matrix with the form e to the minus beta h over the trace of e to the minus beta h. Am I getting this sign right? Yes, I am. We want to do something similar for the best similar notion that we can get for algebraic states. This is a partition function. To do so, we first notice that the notion of a thermal state is intimately related to the notion of what is the time evolution of your system. So in order to talk about equilibrium, you must talk about the time evolution because equilibrium is with respect to some time evolution. If you evolve the system differently, perhaps it would not be in equilibrium. And in regular quantum mechanics, what you have is that an observable A of t is given by e to the I t h a0 e to the minus I t h, which we could also denote as being the evolution of A equals e to the I t h a e to the minus I t h. Now we're going to work with this when we're talking about Gaussian states. One of the about thermal states. One of the properties we're going to have is that if we have the expectation value of AB in a thermal state rho, this is going to be given by trace of A, B, rho, which equals 1 over Z trace of A, B, e to the minus beta h. I may then write this as 1 over Z trace beta e to the minus beta h a, and then insert an identity in here in the form of e plus beta h E minus beta H. This equals then trace of B theta IB beta of A e to the minus beta H, which therefore equals trace of B beta IB A rho, which is thus omega rho B eta I beta of A. Okay, does this calculation make sense?
Nick, there's a question. Does the notion of thermal state depend on the existence of the density matrix?
Yes, we are trying to get rid of the density matrix here. So when you have a density matrix, this is the definition. When you don't have a density matrix, you gotta do something else, which is what I'm trying to do.
Okay, right after the person asks, we can't always find the density matrix.
We can't. There are some situations in which a density matrix does not exist.
Okay.
The notion of algebraic state is more general than a density matrix. So this calculation holds 4 density matrices, and we find that for a density matrix, the notion of a thermal state can be reduced to this idea. So when this happens, it's because we have a thermal state. That is the notion. Actually, when we have a thermal state, this happens. So we're going to define this as what is a thermal state. This is called the KMS condition. Omega of AB equals omega of B theta I beta of A. KMS is for Kubo-Martin-Stringer, and this is our notion of what is a thermal state. At inverse temperature, beta. Okay? Does this motivation make sense?
The person said yes.
All right. So this now works for any algebraic state. If the algebraic state solves this expression, then it is a thermal state at inverse temperature B by definition. Inverse temperature beta by definition. There is still a third class of states we should discuss, which are called the Hadamard states. There is one difficulty that we may face when we're dealing with things such as the stress energy tensor, for example. The stress energy tensor for these sorts of fields is given by this. I think it's a minus for a massless field. There might be something wrong in this expression.
Sorry, before we carry on, just to clarify that you'll always be restricting yourself to the free theory case, right? So these are all algebraic states defined on the free theory.
Yes.
Okay.
Now, when we want to deal with observables such as the stress energy tensor, we have an issue.
One small doubt.
Sorry?
I have one small doubt. Free means, I mean, it can be any free scalar also. It can be. Sorry, free fermionic also, or any spin it can be.
Yes, we could do other theories. I'm doing scalar field theory because that is the easiest one, but it is possible to do similar constructions for fermions and for higher spin fields.
Yeah, okay.
Okay?
Yes.
All right. So when we're dealing with Hadamard states, we have this issue in which I'm now interested in objects that have the form derivative of phi x times beta phi x. Now, if I try to smear this with a function, I'm going to be dealing with something. Let us change to simply phi x squared, which is similar to what is going on in here. If I try to smear this with a function, I'm going to get phi, not going to get phi f times phi f. I'm getting something different, which is phi squared of f, which I have not defined. And hence, we must somehow deal with this. And there's also an issue, because these phi's, they work like distributions. So this is similar to asking me to do delta x is mirrored with fx, d4x. This is going to give me delta 0, f of 0, which is not defined, because it is infinity due to the delta 0. And we want to avoid these sorts of complications, so we must be able to renormalize these expressions. To do so, let me notice that the issue that occurs in here is only as we take the limit of y goes to x, of phi of x, phi of y. Outside this limit, there is no issue with these sorts of operators, because I can smear them with two different functions, f of x, and g of y, for example. But in this limit, in the ultraviolet limit, I do have this issue in which I'm getting to these sorts of expressions which are divergent, and hence I need to renormalize them. In order to do so, we need to have some procedure to do so. Typically, in flat spacetime, what you do is to just normal order the expression. So you just move the annihilation operators to one side, the creation operators to the other side, and at the end of the day, you get a normalized expression that you can work with. However, in curved spacetime, we don't have ladder operators in principle. Given for free. Hence, what we must do is the following. We assume that the state is UV similar to Minkowski state, to the Minkowski vacuum. Since it is UV similar, or locally similar to the Minkowski vacuum if you prefer, it allows us to renormalize these expressions. I'm not going to enter in the details of how we renormalize these expressions because that is somewhat more difficult and involves some more advanced mathematics such as bidistributions and microlocal analysis. So if you want to read a bit about this, you can see, I think it's appendix 2B of my thesis, which is 2305 17453. So in that there is a discussion about how exactly you do these renormalization procedures. But our focus is not every state has this UV behavior similar to Minkowski vacuum. Some of them might be quite wild in the UV, and hence it is impossible to renormalize an expectation value of something of this in these states. So if you ask me what is omega or phi x2, I might be able to answer you in a state that's similar to Minkowski space, to a Minkowski vacuum. But if I take any state, if I take a more wild state, I might not be able to get a finite result out of this expression. So Hadamard states are those states that are UV similar to Minkowski vacuum, and hence we can do this renormalization procedure. As a consequence, these are also the only physically meaningful states. So whatever state I'm working with, if it's not Hadamard, it's not really that relevant. Okay, does this discussion make sense?
So is it right to say that the physical states only give you the closest thing to a vacuum in the Minkowski, but what about the excited states?
The excited states are also going to be similar to the Minkowski vacuum because you are exciting them only in a finite energy. So in the UV, they are still well behaved.
So the notion of Hadamard states also like describe what an excited state could be for the theory. Is that right to
Yes,
say?
correctly.
So only the demand is that when you go very low energy scale, very high energy scales or low length scales, they should correspond to the Minkowski vacuum.
Yeah, at very high energy scales, it should be similar to the Minkowski vacuum. So you can have very high energy excitations, but you can have infinitely many, for example.
Okay.
They should somehow decay as you go to higher energies. Okay, anything else?
There is another question. Is there no way to normalize thermal states?
Sorry, let me. Oh no, all of this three sorts of states, they can be at the same time. So you can have, it is possible for omega to be Gaussian, thermal, be a vacuum, thermal, and Hadamard. So the thing is, we are going to focus on vacuum states that are Hadamard, and some of them turns out to be thermal as well. So it is possible to renormalize thermal states as long as they are Hadamard.
It's okay. No.
Okay. So now we get to our first application, which is the Unruh effect. This is an application in flat space-time, which I'm going to discuss over and over again through different manners. So we start with the metric. We will be interested in a region of Minkowski spacetime, which is called the right-hander wedge. This is given by those points t, x, y, z in R4, such that x is larger than the absolute value of t. Hence, if we draw Minkowski spacetime over here, this is t, this is x, we have over here the curve t equals x, over here the curve t equals minus x, and the hanger wedge r is this portion over here. This portion is interesting because of the following. We have two notions of time translation symmetry in Minkowski spacetime. One of them corresponds to simply moving along time translations. So you just go upwards in the diagram. The second of them corresponds to boosts, which move along the spacetime as this. You have so in this region, moving along a boost is still a way of moving to the future. It is still a notion of time translation symmetry because it is a symmetry, since boosts are symmetry, and it is a notion of time translation because the orbits of this symmetry, when you follow along one of these trajectories, you are moving time in a time-like manner. So it is interesting to check what happens in this region. We will work where
Sorry, are these two the only possibilities? I could have chosen any time-like vector and vector field, and I could have chosen to move along those, right?
Yeah, but we need it to be a symmetry. So it needs to be a part of the Poincare group. You get the options of three boosts along each direction. You get the option
Yeah.
of time-like motion, and the other options are all space-like because there are rotations or
Okay,
translations. Okay.
I see. Yeah, but some combination of this symmetries could also be another symmetry of the system, right?
Yes.
And that could be a time-like vector field.
Yes, but you end up getting either boosts or time translations, to the best of my knowledge, at least.
Okay.
Anything else? Right. So we'll be interested in working with a few different coordinates, which I'm going to define as R, C, C, and that's equal to R, cosh, A eta. With these coordinates, we get the metric ds2 equals minus a2 r2 t eta plus dr2 plus dy2 plus dz2. So while we are working in flat spacetime, this is not an obviously flat metric. It is the flat metric, but we can start to play around with metrics that are not exactly the standard form we are used to. So we're going to use this, which is an accelerating frame actually. So when you pick this sort of coordinates, what you have is that eta is going to be along these lines. So eta equals constant along these straight lines. Sorry, I'm writing Portuguese. While R is constant along these red lines, which are hyperbolae. As a consequence, if you pick R equals const, this is an observer moving along a boost trajectory. It can be shown if you write down the vector for boost, which is, if I remember correctly, this is a T, AX, A. You can show that the acceleration of this is such that AB equals A squared, where A is this constant here, and hence it is constant. Therefore, R equals 0 or R equals a constant means that we're following no, R equals 0, I don't think it is possible. But R equals a constant, a positive constant, equals to an observer moving with constant acceleration. What is interesting then is we can pick what is the 2-point function for the Minkowski vacuum. It is given for a massless field by this, not smearing it. By W lim, I mean that you should take the limit only after you smear it. And T mu is an arbitrary time-like vector. This is the expression. We can then rewrite this in R phi coordinates. I'm not going to do the complete calculation, but what you can do at the end of the day is you focus on phi f, phi g, and it can be shown, see the lecture notes for a few more details, that this is going to be phi g, theta I beta, phi f, plus everything. Okay. This can be shown by showing that by translating alongside the eta translation. So if you write this in terms of the r and eta coordinates, you will be able to show the W2 x1 theta t plus IV x2 equals W2 theta tau x2 x1. Is it? Yes.
So is this the W is the Whiteman function, right? It's not the
Yes.
Feynman correlative.
Yeah, it's the Whiteman function.
So I'm not aware of it, but how do you find Whiteman functions for fields?
We define them for, oh, sorry, yeah, so, oh no, yes, this is right. This is, something like this, actually. Yeah, it's mirrored.
No, I was just asking, like, is how do you obtain the expression, the first expression that you wrote down, W limit that 1 by
Oh, these you can get from Bogolyubov.
Okay.
So it is just in the literature, and I didn't derive it.
Mhm. Is this expression background independent? Like for any background, this holds?
No, this is only for Minkowski and for the Minkowski vacuum.
Okay.
So what you see at the end is that for the Minkowski vacuum, we have the KMS condition when we're working with time translations over this region. Okay?
And what was the T in the denominator? There was a
Where?
T mu.
Oh yes, this is an arbitrary time-like vector. All right? And hence we get to the KMS condition, which means the Minkowski vacuum, the usual one from flat spacetime QFT, is thermal for accelerated observers. This is called the Unruh effect. Does this statement make sense to you? It should be somewhat shocking, actually, because we're used to think of vacuum as something that is empty. And what I'm saying is it is not empty, it is actually a thermal state. So you do get particles in this state. And these particles are in a thermal distribution for an accelerated observer. So the notion of a particle for an accelerated observer is different than the notion of a particle for an inertial observer.
So this notion that the vacuum is not unique, one can think of this as this being a reason because the accelerated observers are also not unique. You can choose different accelerated observers.
Sorry,
Is that
I
right?
didn't understand the question.
Previously in the lecture, you concluded that the Minkowski vacuum is not unique. If I understood right.
Yes, it is not
So
necessarily unique. There
oh
are a few
no,
details,
okay.
but
Okay. My question is the reason that Minkowski vacuum is not unique is because the notion of accelerated observers is also not unique because you can choose different accelerated observers.
no. What happens in here? Oh, by the way, I should have mentioned that beta equals 2 pi over a. So the temperature is a over 2 pi. The faster accelerates, the higher the temperature. But no, it's not related to having different accelerated observers. What happens with the vacuum not being unique is simply that I can choose different options that are still Gaussian and pure. So for example, I can also choose the Handler vacuum, which is defined as 0 Kelvin for accelerated observers. So this is a different option for a vacuum. However, this is not Hadamard. When you get close to this boundary in here, the Hingle vacuum fails to be Hadamard. So this is only Hadamard in this inside region. But this is also Gaussian and pure. So in Minkowski spacetime, we can say that the Minkowski vacuum is sort of unique because it is the only Poincare invariant state, and it has this state that minimizes the Hamiltonian for an inertial observer. So in some sense, it has a taste of uniqueness in Minkowski spacetime, but in other spacetimes we have more than one option of vacuum.
I have
Sorry, could you
one doubt.
cover again why the Rindler vacuum is not Hadamard?
No, it is not Hadamard. It fails to be Hadamard at this boundary region where t equals x and where t equals minus x. It is not Hadamard. So it fails to be Hadamard in this red boundary.
Excuse me,
I mean,
one question.
Sure.
Is the boundary a set with measure 0? Should we expect states that are not Hadamard there to behave in some way pathologically?
Yes, because in this region, we won't be able to renormalize this rest energy tensor, which means that we get infinite energy density in here for this state. So it kind of doesn't make sense. You expect at least for you to be able to renormalize this rest energy tensor and get 0. And this is not possible in this region.
Okay, got it.
Like if you have like, is it for only if you have only scalar field, like if you have two kinds of field, let us say some scalar and some fermionic, is it not possible that like both divergences cancel each other at right at this boundary?
Sorry, I didn't understand your question.
I'm saying that we are getting this kind of divergence at the t equals to x, t equals to minus x. If you have some Minkowski vacuum field and this divergence is in Rindler frame. So if you have two set of fields, not only scalar field, massless scalar. So can't we normalize with the help of more fields?
If I had two scalar fields, could I have something that is Hadamard for
Yes,
one of them, but not for the other?
yeah, two or more other fields other than scalar.
Yeah, I think it is possible for you to have a state that is Hadamard for one field, but not for the other. That's your question.
No, I'm saying this is not Hadamard if I have only one field. If I have superposition of other, so can't more divergences cancel each other?
Oh, if
I
adding
mean,
more
if there's
fields can
energy,
make this state become Hadamard.
yes, because if you have only scalar, then we have divergence of stress tensor on the boundary. But if you have more field, then can't we have regularize this stress tensor, because both divergences can cancel each other.
I'm not fully sure, but I believe that's not possible. I think that if you add more fields, you're just gonna make the situation worse.
Okay.
Anything else?
Yeah, I have one more question. Like you said that Minkowski vacuum appears a thermal bath or a Ringler. You didn't say what does this Minkowski observer to this Ringler vacuum, and how does this Ringler vacuum look like to a inertial observer?
How the Hingler vacuum reflects to an inertial observer.
Yes, yes.
Not actually sure, but the inertial observer will surely see particles. It might or not be
Yeah.
thermal, I'm not sure. But it will
Okay.
definitely see particles.
Okay.
One of the ways of understanding this notion of why you can have different observers seeing or not particles is the following. The notion of particle in QFT is given when you decompose the field in creation and annihilation operators. And you're going to have something like e to the minus px ap plus z to the plus ipx ap dagger. Is this 3 or is the 4? Yeah, I'm gonna just put D in here. So this one is positive energy. This one is negative energy. So you see that the notion of positive or negative energies is what allows me to define what are the ladder operators. So why is this important? Because energy is the netto charge conserved by time translation symmetry. If I have different time translation symmetries, such as inertial and accelerating, then this implies different notions of energy and hence different definitions of particle. We'll see this in more detail in the next class. But the main idea is this, in which different time translation symmetries, so you have an inertial moving observer and you have an accelerating observer, they have different notions of time translation symmetry. Hence, they have different notions of what is positive energy. And since they have different notions of what is positive energy, they have different definitions of what a particle is, because a particle is an excitation with positive energy, while an antiparticle is related to negative energy modes. And hence this is the basis of what leads to this weirdness when one observer sees no particles at all in the state and it is freezing to death at 0K, while another observer is seeing particles at a Fermi distribution proportional to their acceleration. They agree that it is the same state, but they disagree about what are the features of this state. This is similar to how, for example, in special relativity, you can agree on what is the electromagnetic force, but you can disagree on whether the force has an electrical or magnetic origin. Does this make sense?
Nick, Dominic has a question. In the Unruh effect, are there partner particles outside the right Rindler edge?
That's a great question, and actually there are. You can relate the modes on that are over here, and they are entangled, for example, with modes over here. Or actually, yeah, this is one of the possibilities. Another possibility is you have a mode on the right hand side and you have a relation with what is going on the left hand side. For each particle you see on the right hand low edge, you also have a particle on the left hand low edge that you're not going to observe. There is a wonderful paper on this. Let me find it real quickly. More 2019. What the hell is this? Oh, here. Let me throw this in the chat. Why can't I open the chat? This archive paper discusses it beautifully with other goals, but it is, oops, sorry, I sent in a direct message. Now we go. You're welcome. It's 19. What is what I just wrote? (1908) 06363. Any other questions?
Nick, I think it might be a good time to link the attendance list. I don't know if you have it ready
Oh,
or
yes.
if I should create
I
it.
completely forgot about it. Thank you for reminding me. There it is. I think the paper that Bruno is signing is probably the reason why Wald wrote the paper I sent. Okay, any more questions or comments?
Yes, one small thing. If particle number is no longer an invariant for different observers, does that mean that different observers have to define ladder operators differently within the regions of spacetime?
Yes. And that is exactly why I'm not working with ladder operators.
Right, makes sense.
So it is possible to work with ladder operators in curved spacetime, but you have to be careful about these things because you have different notions of ladder operators for each symmetry you have. And if you have no symmetries, you might not be able to pick a preferred notion of ladder operators. So it is a more subtle way of working, but the algebraic approach, it completely evades this issue by working directly with an algebra instead of working with the ladder operators. Great question. All right. Unless there are any more questions about the Unruh effect, I'll move on to the Hawking effect, which is actually in curved spacetime, although I will not do the calculations in detail. Okay. So the Hawking effect. Another interesting scenario is what happens when we are close to a black hole. And what exactly are we going to see in this situation? The first scenario I'm going to pick is an internal Schwarzschild black hole. Notice there is also a cross in here. This is very relevant. This is called a bifurcated Kelvin horizon, which is what we had in the Unruh effect, where we had this cross over here. And whenever you have such a cross in a well-defined manner, so it is the limit of some healing field that is working like this, such as we have here in Schwarzschild with the time-like healing field. This is known as a bifurcated Kelvin horizon, and you're going to have some interesting properties, in particular thermality. So in this situation, we have an eternal black hole. There is a single Hadamard in stationary state. Whenever there is a Hadamard stationary state in a static spacetime, it is a unique state. This is called the Hartle-Hawking state. Or Hartle-Hawking vacuum, if you prefer. The behavior of this state is the following. You, who are standing outside the black hole,
Sorry, could you define what is stationary?
Stationary means that I am in a static spacetime, so the spacetime does not change with time. And static actually means it is a bit more structured than only not changing with time. And static does not mean rotation.
Okay, so the stationary here refers to rather than the something to do with the Hilbert space.
No, yes, it refers to the space-time and it refers to the state. So the state does not change with time.
Oh, okay. So it's the usual quantum mechanical stationary state.
Yes.
Okay, fine.
And then we have this Hartle-Hawking state. The behavior of the Hartle-Hawking state is that if you're here in a static trajectory, so you are following the time-like healing field, you're going to observe thermality coming from both the black hole region and from infinity. Actually, you have to observe from the past.
Nick, Dominic has a question. Could you repeat the definition of the Hartle-Hawking state?
It is the unique Hadamard stationary state in Schwarzschild spacetime. Does it make sense?
He said yes.
Okay. So the Hartle-Hawking state you are going to observe, it is a thermal state. I never remember the temperature by head. Let me see if I wrote it in my notes. Yes, I did. 1/8 pi m. With temperature 1/8 pi m. For static observers. So observers that are sitting at a fixed distance from the black hole.
Sorry, just a quick question. The Hartle-Hawking state is the vacuum state with respect to the Schwarzschild time, right?
Yes, but if you're following the Schwarzschild time, you are going to see it as being thermal. So this is an interesting feature of it. An inertial observer will not see any particles, though.
I see.
a common argument for why this happens that I consider a wrong argument, and I'm going to explain why in a few seconds, is that if you are a static observer, then you're staying in a few minutes actually, then you're staying accelerating away from the black hole. Hence, due to the Unruh effect, you're going to observe formality. And this is essentially the formality you're going to watch. And oh yes, and this value is for observer at infinity. Otherwise, you have a correction due to the redshift. And this formality is coming from the black hole. And from infinity. There is now a more interesting scenario. Suppose you have a star that collapses into a black hole. Let me change the coloring of this. In this situation, what we have is similar to this torsive diagram. We have the star in here, and everything in this yellow region is part of the star. So it doesn't really exist. There's no white hole, which would be this lower bit over here. There's no parallel universe over here. Instead, all that you get is our universe and this black hole. What is interesting about this is that we can no longer use the Hartle-Hawking state. Instead, because the Hartle-Hawking state has modes coming from the white hole. Up into the universe, which no longer exists. So since this region does not exist, these modes can no longer exist. Hence, we have to use some different state. Luckily, since the past horizon, this region over here, no longer exists because the star is covering it, we can pick a state that is not Hadamard in here. So it is Hadamard in this spacetime, but is not Hadamard in this spacetime. This is called the Unruh vacuum. It is not Hadamard in the past horizon. Which does not exist. It is formal at t equals 1 over h pi m. With modes coming only from the black hole region. Not from infinity. This is known as the Hawking effect. The previous effect in shorter spacetime that I described is actually the Unruh effect in curved spacetime, but some call it the Hawking effect. Curved spacetime. I don't like all the Hawk effect, or how do I make this again? You have these two different scenarios. Let me just move my phone here. There's still a third one. Now we pick a star that does not collapse in a black hole.
Sorry, just a quick question regarding the Hartle-Hawking state. So you said that
Mhm.
the thermality had to do both with the horizon as well as the is infinity. But
Yes.
I don't understand why the infinity has to play any role.
It's a
I
property
mean,
of
both
this
the
state.
the thermality had to do with black hole and the spatial the infinity. So what does infinity have to do with it?
This is a property of this state. Just like in the Hindler case, we had an accelerating observer and it had thermality coming from all around him. So he feels modes coming from behind him and from ahead of him. So if he's here, he does feel he's getting warm from both here and from here. So this is just a similar thing that occurs with the Hartle-Hawking state.
Yeah, but the Hartle-Hawking states were constructed out of modes just from the modes that fall into the black hole and the modes that come out of the white hole. So I
No, it is
don't
also
really
constructed
understand.
out
Like,
of it is also constructed out of modes that come from infinity.
I see. Okay. Okay, well, that makes sense.
Okay. The Unruh vacuum is this different one in which it only comes from the black hole region. I don't think there is a diagram for where exactly it comes from, but it comes from within this region. And there is still a third interesting case, which is when you pick a star that does not collapse into a black hole. In this case, we have no horizons, but the Unruh vacuum has these modes that fall within the black hole. Hence, we cannot pick the Unruh vacuum out. Instead, what we have is this diagram where everything that is in yellow does not exist due to the star. Hence, we can pick a vacuum that is not Hadamard in either of these red regions, in either of the horizons. This is known as the Boer vacuum. And it is the reason.
Nick, there are
Yes.
a few questions. The first one is, can the non-existence of Hartle-Hawking state for a collapsing star be imputed to the fact that there is no stationarity anymore?
Um, I consider it a fair argument. I'm not completely sure, but I think yes. I think so.
Okay, there's another question. Is there a uniqueness claim for the Unruh vacuum?
Mm, I'm not sure. I've never heard of another vacuum that was similar to the Unruh vacuum. So I think it is unique in some sense, but I'm not sure how I would state this uniqueness result. And I'm not completely sure whether this is unique in some sense or not. I believe it probably is, in some sense that I'm not sure how to write it. As for the lecture notes, I saw that someone asked here. They are already available in the website. Let me pick them for you. They're available in here. But I'll see if I add them to the folder as well. So this is the Bohr vacuum. The properties of the Bohr vacuum are no formality, or 0K if you prefer. So no modes coming from anywhere. Notice this is, I mentioned a star, but it could also be a planet, for example. So this is the reason why when you have a star or a planet, we don't talk about Hawking radiation, because it's a completely different vacuum state. And as a consequence, that argument about being accelerated and hence using the Unruh effect does not really apply. So it is way more subtle because you have to consider what is this the state you're actually working with. Yes.
Yeah, I'm asking like you said static observer and hydrolocking vacuum observe some thermality. Like
Sorry, I'm
and
not
you said that
understanding.
you said that in hydrolocking vacuum, a static observer at infinity observes some thermal radius and thermality. But in ball vacuum, there is no radiation for a static observer. Can a moving observer or accelerated observer in uh, ball vacuum observe some radiation, some inertial observer?
So why there's no incoming radiation for the Bohr vacuum?
So that is for a static observer. No?
It's due to the absence of a horizon. The horizon is what makes the thermality. And in the case, even in the case of the Hawking vacuum, it is the existence of the horizon that guarantees they're going to have thermality, even coming from infinity.
Yeah, but even if in hydrolocking we have horizon, but if you have some inertial observer really falling to the black hole, even there is horizon, he doesn't observe any thermality. So like in this case, inertial observer free falling doesn't observe any thermality. So I'm asking, is an ball vacuum freely falling or inertial observer observe something?
Yes, the Bohr vacuum has no thermality because it has no horizon.
Okay.
So the star just covered all of the horizon, and you have only the star. So the horizon does not exist in this case.
Mm.
Does it make sense?
Yes, sir.
Okay. Well, let me see whether there's anything to discuss today. Yes, and I think here's where we stop today. There's something else I want to mention, which is a criticism of the algebraic approach. So as we previously mentioned, there is this difficulty with choosing ladder operators because we have no clear notion of particles when you're dealing with curved spacetime. Hence, this is one of the advantages of the algebraic approach, which is what I've introduced so far, and why exactly I like to use it. And it is more difficult, however, to do calculations with this approach. So it is more of a proving theorems style of doing QFTCS rather than doing calculation style of QFTCS. However, it has this advantage that it does not rely on you choosing a notion of particle, which would be a choice. So it would be putting the physicist ahead of the physics. And these are basically its advantages and disadvantages. So are there any more questions for today? Okay, apparently not. So I guess let me just check the chat. All right, Bruno sent a paper on the uniqueness of the Unruh vacuum. All right, I think that's it for today then. Thank you very much for your presence. I'm going to stop share and see you Monday.
Monday. Take care.
Take care.